Hello and welcome back to Precalculus 1. We're almost done with the semester. Crying yet? Yes. We have applied section to work on today, which is going to utilize previous section solving equations. The first thing that we are going to work on is, let's say, population. Then we can do something with money and finances. Then we can move and do some environmental problem. You have to understand, hopefully once you did your class preps, you understood already that exponential functions and these problems that we are going to do here touch almost every aspect of our lives. You can find these exponential functions anywhere. So we are going to take a look at sciences and physics and engineering. We are going to take a look at population, which is biology related. We're going to take a look at the money and finances, right, which is business and economics related. These exponential functions are everywhere. Even if you think about carbon dating, which is going to be using these equations, carbon dating, to find how old stuff is, that would be, again, right, exponential functions, which is the area of history and archaeology, so on. So almost every aspect of our lives is governed by these functions in some sense, so we can find a lot of easy examples. What I'm going to start with is first write that the main formula is y equals a e to the kt. So that's the main formula. And then you have these two situations where the graph looks like this, which is k larger than 0. We call it growth. And then we have a graph that looks like this, where k is less than 0, and we call that decay. The y-intercept is this a that we have in the equation, and the x-axis is actually t-axis because everything is in terms of time. So that will be independent, right? And you have your y-axis, which is the output. Now what I'm going to do is I'm just going to take this formula and write it in the terms of things that we want to explore. For instance, population at any time is initial population e to the kt. Or let's say you have that the mass time t is equal to initial mass e to the kt. This would be the decay of garbage or radioactive elements and so on. We can talk about finances where the amount is equal to principal times E times RT, which is money. There are many applications of these exponential equations. So let's start with population. Get the depressing one out of the way first. So I'm going to show on the main computer here population clock, which is I gotta switch. So population clock, it shows you population in the United States, it shows you population in the world. You see that population in the United States grows 1 birth every 8 seconds. That's just United States, US population. No, that's the world, sorry. 10 most populous countries, China, India, United States on the third spot. Followed by Indonesia. That's Rafael is from Indonesia. They have thousands and thousands of islands. 4 billion in Indonesia. Brazil, a fifth of a billion. It's a large country. It is so interesting to see one of the tiniest countries in the world make the top 10 list in population, Japan. 126 million. That's a lot, right? So when you look at the countries, right? Pakistan, Nigeria, Bangladesh, Russia. Most of them are really large countries, and obviously populations are large. So we are looking at 7.352, right, in terms of the billions. And there is a concept, it's called carrying capacity of the planet, which, depending which school of thought you read and choose to believe to, could span anywhere from 10 to 15 billion. What's the carrying capacity? What do you think? It's the maximum number of people you can sustain on our planet. It is calculated looking at the resources needed to feed the population, clothe the population, shelter the population, and so on, which means land for housing, for growing food, also getting the natural resources in terms of coal and oil, because you're still burning dead plants and animals for fuel. And then energy requirements, obviously, in terms of electricity, because all of you want to be busy with your phones right now and laptops and so on. So you have to charge those batteries. So there's a lot of energy requirements on the population. So we can use this model, population model, to approximate at what point we are going to reach, right, what is the year when population is going to rise to whatever number you want to take as the carrying capacity of the planet. So let's say, so current population, which is 2016, so current population is 7.35. Let's go 2 decimals. So in 2016, which is the input point, population is 7.35 billion. No, this is one of the points. I will. I just need to show my in-depth research. Now let's take a look at world population in 1980, let's say. Something, 1980. Look at that, 1970, half of what we have. We doubled the population in 40 years.
Oh, look at the 1990, what is that more?
4 billion.
1980.
I can't see that far.
So 1980, 4.43 billion.
What's that? This total growth?
10-year growth rate, so it shows percentage by which it grew. So let's say that you want to know population in what year in the future? 2020? 2030. All right, so the first thing that we should do is what you guys usually did on your labs so far, I hope, is to take these years and zero them out, right? So the lowest number we have is 1980, so we're going to set that to be t equals to 0. If 1980 is t equals to 0, then 2020 is t equals to 40, and 2030 is 50. And how about 2016?
36.
Yes. Okay. So let's start. Population in time is initial population e to the kt. We have our initial case over here because that's when the t is 0. So it's like starting the time in this year. And then what you do is you plug the values that you have into your equation. So you know the population is 4.43. You don't know what P0 is, but you know it's e to the k times t, but t is 0. From here, you can immediately figure out that P0 is equal to 4.43, which is initial population. You will know that in two different ways. First of all, any point that contains t equals 0 is initial point. So its y value must be the P0 where we need for our calculations. So now that I have P0, I can compile the model P of t is equal to 4.43 e to the kt. I still need to figure out k, which is what you have the other point for. Remember, you have a point that says 36, comma, right? This one over here, this point. So you use the initial point first to get the initial population, and then you use whatever other point is provided to you to come up with the equation for the problem. So that's what? 40, what was it? 36, 7.35. All right. So this is just a point that is given to us in the text. So now I have the equation, I have the y value, I have the t value. I should be able to calculate k because that's the only variable we have. So population is 4.43 is equal to, no, sorry, 7.35. 7.35, that's the y value, is equal to 4.43 e to the k times 36. I hope you see exponential equation over here, which we know how to solve either by conversion or solve it by using the ln, both sides, whatever works. I'm going to divide both sides by 443. Remember to keep 4 decimal places. So these guys cancel. We get that e to the 36k is equal to whatever we get when we divide 7.35 by 4.4. It's amazing that I can't get the calculator to work. 7.35, hopefully it works better. Do we all get 1.659?
Yeah.
1? 4 decimals? What happened? Bless you. So now we have a situation where we could use the conversion, or you can put the ln both sides. If you put ln both sides, then you need to know that the exponent jumps down. If you use the conversion, you need to know that ln is the log base e. So you have to know something either way. If I ln both sides, then ln and e cancel. I get 36k on the left, and on the right I can punch this number in, ln of 1.6591, and get 0.5063. Remember to round properly. There was a rhyme, yes. Very good. Which means you're paying attention. I was about to rhyme again, but then it would be just too much. And I would kill it, so no. K equals, we will divide both sides by 36. So 0.5063 divided by 36 to obtain 0.0, and now 4 decimals, 4 significant, right? So it's going to be 1406.
So when the zeros in the front, you have to put 5 decimals.
Or 17 if you have 12, right? So depending on, it's four significant, right? The ones that are non-zeros. I am finally able to write the model. Population at any time t is 4.43 e to the 0.01406 times t. This is what we call mathematical model. And in this case, the math model of world population. So now you want to know what's happening in 2020, which is in 4 years. Well, this says that the t is equal to 40, because 1980 was our 0 year. Then this one is 40 years later. So all you need to do is to take the equation that you have and plug in 40. Tell me how many, what's the population? Go. One hundred. 179 billion. Can it be 100 something billion? How much? 7.7. There we go. I have no clue. What are you guys computing? But P for 2020 is going to be 4.43 times E raised to the 0.01406 times 40. With the proper use of parentheses, you should have this in no time, as they would say. I don't know what that means. No time sounds stupid, but yep. So population in 2020 will be 7.774111 and so on billion. It's only 4 years from now, right? How about you compute on your own for 2030? Go.
Yeah, whatever.
No, we use the same equation, just change 40 for 50, that's all. And depending on how well you use your calculator, you can plug all of this at once. It goes 4.43 times, you type in E, then you do the little caret, and then you open parenthesis,
Oh, Shabby.
and you go 0.01406 times 50. Everything can be done in one less. You are excused. Millie.
God bless me.
Yeah, I did. All right. I know. So what's the population? Yes, it's a lot. So we have 8.95 billion. And you see that's in 12 years, right? So if the carrying capacity of the planet is 10, carrying capacity of the planet, guys, is actually changing all the time as more industry, as more, right? Yeah, all of that stuff. So there's a lot of factors. Let's talk money. Anyone wants to buy a car?
No. I
Great.
got one already.
Tesla Model 3.
I already have a car. Thank the Lord for giving me a car.
Okay. So let's talk about a car. Say you want to buy a car that it's how much money, but be realistic because we want to find out something that actually makes sense. So
28,000.
20. Okay.
20.
20. You said 20,000.
We did that last time. We did 20 last time. For a car 30. Do 28.
28 too much. 30 too much.
28.
22,
28.
22, Jerry, 22.
28.
Which number should we use?
28. That's not logic. That's like 1 year old. 28.
Can I get an 80,000 for a range?
It's $1,000 for that month. Let's go and
32.
$28,000, the loudest person here. What's your down payment?
I got 7,000.
Good, medium, or bad credit? You want to do 3 years, 5 years, 6 years, 7 years?
3.
5.
5.
Guys, he's listening to me.
Really
Yeah, I just
though-
ignored everyone else.
Really though, 4% for bad for good for medium credit.
You get two.
3.5.
You can get yeah, but you can get good credit with 2.6% or something. It doesn't matter. Okay, let's go. So what do we have? We are going to figure out the actual number, and we're also going to figure out the approximate number. I want to do the approximate number first because it's easier, because we are going to use exactly what we did so far, which is the exponential with e. So the amount you owe is the principal you borrow times e to the rt. So the principal you are borrowing, well, if we want to be exact, right, you will have to calculate in the tax and then subtract. So, you know, I'll say go, and I'll say plus tax. So that's 1.7. Yes, we are multiplying by 1.07. So we have 28,000 times 1.07, which gives you 29,960. But then we have to subtract 5,000 from that because that's the down payment. And then we have e to the 0.04 times 5 years. So we plug everything in. So this was,
How much was tax?
I'm
I'm sorry.
sorry?
1.07
Oh.
for tax.
Yeah, 1.07. Yep, 7% in New Jersey. Unless you are from a different place.
Wait, why is there 1?
1 keeps the amount and 0.07 adds, so you don't have to, so you don't have two calculations. So what do we have? 24,960 e to the 0.2. And now you compute this, take the abacus and just punch these numbers. 24,960 times e raised to the 0.2, and the amount you owe is 30,400. So this is the worst case scenario, and 21 cents. Now monthly payment will take the number 30,486 and 21 cents and divide it, because it's 5 years, into 60 payments. And we get at 508.10 cents. So $508. Now this is the worst case scenario, because compounding is done all the time. This is called continuous compounding, which means that the interest rate is computed at all times since you take the loan throughout the 5 years. The reality is to use what we call the compound interest formula, which doesn't have E. So that formula, which you must know, is A equals P, and then 1 plus R over N raised to the NT. So P is the principal, R is the rate as decimal, and N is the number of compounds. I'll talk more about N. And then T is time, usually given in years. Now, what is this compounding business? Well, certain things in a business world occur with a certain frequency. For instance, taxes and earnings for companies is provided on quarterly basis, so every 3 months. You do your taxes once a year, which means annually. You get paid maybe every other week, which is known as bi-weekly. So you have 26 checks in one year. But you pay your credit card bills and most of the other stuff when? Every month. So that's monthly. So this N is how many of these payments throughout the year you're going to make. So for taxes, it's one payment, so it will be one. Quarterly, that's 4. But most of the time, you guys will be dealing with monthly. If you take a student loan, car loan, you take a loan to buy Apple garbage, right? No, people do that. It's sad, but people do that. Serious. Then N is equal to 12. All right? I get my apples at farmer's market. Yes? 60 months in 5 years, 60 payments, because it's we're calculating monthly payment within 5 years. 5 times 12 is 60. So now we are going to use the same parameters here to calculate the exact amount for this particular car. We still have the principal to be the same, 29,000, what was it? No, 24,960. That's after tax and the down payment and all that. R is still 4% for easy calculation. And I'm going to use N equals 12 because I will be paying back car every month, right? And we're going to use 5 years. So all you need to do is to plug everything in. Amount you owe is the principal, which is 24,960. Open parenthesis 1 plus 0.04 divided by 12 raised to the 12 times 5. This is 24,960, 1 plus, and now you can multiply top and bottom by 100, so that will be 4 over 1,200, and then divide by 4, so 1 over 300. When you simplify it, raise to 60th power. And then use abacus to figure things out. You can type everything in if you're good with parentheses. So you type 24,960, open parenthesis 1 plus 1 divided by 300, and then little caret, and then 60. When I simplify the fraction, multiply top and bottom by 100, and then cancel 4 and 12. So we get 30,476 and then 7 cents. So monthly payment is going to be 30,476.07 divided by 60 payments. And the exact amount is 507 and 93 cents, where the approximate amount was 508, 10 cents.
Why do you divide by 6?
Why?
5 years, right?
Yeah.
Where do you get the 12 from?
That's months.
Oh,
Number of compounds. Number of compounds.
Number of compounds.
but what's the compound?
When you compute the interest.
How do you say your first
Using my mouth.
name? Can you pronunciate it for me?
Yes. Nemanja.
Nemanja.
All right.
Say your last name.
Ch. You gotta be cool about it. Flat. So what we have here, our first two introductory problems, we did the population and we did some of the finance, which means car payments in this case. You can do it with student loans, you can do it, you know, not mortgages. Mortgages work differently, they're much tougher. So now we're going to switch our gears and take a look at the environment, for instance, or history or so on. Before we get into these calculations, I will take some time to explain first what the meaning of half-life is. Yeah, I know everyone is waiting for the Half-Life 3, sure, but wait. Let's talk about Half-Life here. Have you ever heard that joke, well, those of you who are into Valve and so on, that it would be awesome if actually Gabe was elected the president. You know why? Because the World War III would definitely never happen. There's no Portal 3, there's no Half-Life 3, there's just, we're waiting for years and years. There's not even an announcement of any of that. So if Gabe was the elected president of US, definitely no World War III. Don't worry about it. It's just,
like, are you talking about some nerdy stuff right now?
Yeah, it's nerd stuff.
Alright.
Yeah, it's cool stuff. Don't worry about it. I'm talking to 4 cool students, that's it. Oh, you feel left out? Start playing video games daily, every day.
I have like more stuff to do with my life though.
What? Look at YouTube videos with makeup tutorials?
At least it's using everyday life.
All right, there's just chaos over here. As soon as I mention video games, this is what happens. So, all right, back on track, everyone. Let's do the great shusher. Excellent. The shusher worked great. So now, half-life. So half-life is denoted by lambda. Yep. And we have to lambda.
Got it.
Lambda is the Greek symbol that it's equivalent to our L, right? And that's the symbol right there, so practice it. So it looks beautiful when you, not if, but when you use it on your exams. Lambda? No, there are other letters like mu and sigma, and so not lambda. All right, so now what we are going to do is I'm going to write the definition for half-life. So, and you need to know this one, otherwise you're doomed. Half-life is a time in which half of the original mass decays. This means that if this roll of paper here has half-life of 10 years, that means that if you wait 10 years, half of this roll of paper would not be there and half would remain. Then you wait another 10 years and the half of the half would go away, which means a quarter this time. So it is exponential decay.
Does it eventually all go away?
No, because the decay problem, and you will see what are the implications of that. If you look at the decay graph, you see how the amount, which is on the y-axis, right, as time goes on, that this is asymptotic behavior, that this line never crosses the x-axis. That means that it never goes down to 0. It does go to 0 in the limit, which is what you study in calculus, but not in a sense of Precalc doesn't. So now, what we can do with the half-life calculations? Well, we can do, as I said, history, which is archaeology. You go and you dig up something old somewhere, right? And if there is any kind of organic material on it, you will be able to do carbon dating. Carbon dating takes the isotope of C14, carbon 14, which has the known decay rate, and just by figuring out how much carbon is left, you can find out how old the object that you are looking at is. It's good to carbon date paintings because in old times everything was made out of all of the paint was made directly from flowers, which is organic. You can dig up some old wooden spoons and then maybe plates or whatever. You can't carbon date pyramid because pyramid is made out of stone. There's no organic material. However, if there are pyramids under the sea, like those the coast of Japan, you can actually, drill all the way down to the stone and then take the bottom layer of coral and then carbon date that, because that will be right. The coral growth happens when you put something in the water within the first year of its existence already has a coral on it. So carbon dating is one of the things that we can do. So half-life will play a role in that. We can also take a look at the garbage disposal. So we're talking about environmental science right now, which is one bag from ShopRite or whatever will take let's say 10,000 years on half-life to lose half of its mass, right? And the other half of the time, the turtle is going to wear that everywhere. You have that part, so plastic, right, or anything of that sort. So garbage decay is a big issue because there is we produce a lot of garbage. And then we can also talk about radioactive decay. Again, environmental issue, right? When one of the nuclear plants goes kaboom, there is a lot of issues, right? You have the Chernobyl, you have all the other ones that happen in US and Japan and so on. Whatever is the of radiation that was spread around, you can do these same calculations to see if those regions will be habitable in any foreseen future. But also you can use this to figure out decay rates, right, of the elements and so on. So you can do science with it and so on. So we're talking about science and environment and history. So again, a large spectrum. And then there is also a huge medical application, because anytime you take any kind of medication, a drug, right into your system, it is going to metabolize in the system using exponential decay. So we'll talk about that as well. So now we have a wide range of application. Let's do something. How about we do medical application first? So Advil. Shall we do? Let's do Advil. All right. I'm going to go. Let's see. Wolfram Alpha. I want to see just stuff on Advil. All right. So if you haven't known so far, Wolfram Alpha, right? The math software has knowledge database about anything in the world that has any kind of number attached to it. So this is what they know about Advil, which is ibuprofen, right? You get the formulas and stuff. You want to cook it on your own. And then, yeah. Wolfram Alpha. I think.
Yeah, I think so.
Okay. And now, if you, so you have all of these, they tell you how it interacts with others. Ah, there it is. Biological half-life, right? So we're talking about metabolizing Advil in a stream. And look, it's 2 hours almost, right? 1.9 hours. What they say about dose, right? You take Advil every 4 hours, right?
What's the milligrams on that one?
That doesn't matter. We'll see. We'll see why. Well, yeah, actually, half-life is standard no matter how much you take. It's just how much the body can metabolize. So that's the overdose comes in on that end. But let's just see how this works first. So say you take whatever dose is, 2 pills, 400 milligrams, whatever. But look at this. You have that the mass of Advil in a system is initial mass, which is how much you took, times e to the k t. Now we know that lambda is, let's just say 2 hours because it's easier than 1.9. So now, what do I know from definition in red, which is right above the equation? I know that this is the initial mass, the original mass. Maybe I should use initial. Let me use initial rather than original. So this is the initial. So what's left is half of it. So I have mass divided by 2 is equal to mass e to the 2k. Because t, lambda, right? Lambda is time, which is 2 hours. So t is you know what? Let's go k lambda, and then we'll plug in the value. Notice that mass cancels. So whether it was 100 milligrams, 200 milligrams, 400 milligrams, 30 tons, in terms of how fast it's going to metabolize, well, no, that's the equation there. We have 1/2 is equal to e to the 2k, and then we ln both sides. This is e. Looks ugly, but it's e. And we have ln of 1/2 is equal to 2k.
What
And
happens to the lambda?
lambda is 2.
How is that possible?
Well, she was the half-life.
Then why would you put the lambda next to the k originally?
Lambda is time.
If you wanted it to show why we were plugging in.
Yes.
Why does the element make black? Alright, okay.
Cool.
But then why does the ln stay with the half?
That doesn't equal.
You ln both sides.
Yeah, I know, but the ln goes away.
ln cancels e.
Why do you divide by 2?
Because of the
Divide half of the initial mass. So this is the mass at any time, fair? And this is the initial mass here. So now, if I am to use lambda here for time, if I'm to use lambda there, then I have to use half of the initial mass at the same time. I have to put that. All right, so what do we have? We have that k for Advil is where is it? I have ln of 0.5 close parenthesis divided by 2 negative 0. Remember the 4 decimal? 0.3466. So what do I have as a model? Mass of Advil that it's still in a system is equal to the initial mass of how much you took times e to the negative 0.3466 times time. That is the equation for Advil, for metabolizing Advil in your body. So now, what's happening here? Well, you say, I want to know how much Advil is left in, I don't know, after 3 hours, after 3.5 hours, after 4 hours, after 5 hours, right? So thinking about that, you can just plug in the value t and time, and then you know how much you took, which is 200 milligrams, 400 milligrams, whatever it was the dose, and then you plug all of those in, and you can compute. But you can also ask, and this is one of my favorite questions. Let me ask this question right now. How long do we need to wait so that 99% is metabolized? So I want to see how long does it take for 99% of whatever I took, whether it's 100 milligrams or 400 milligrams, 500 milligrams, how long do I have to wait until 99% is metabolized? Well, let's see. We put, and t is in hours. You have to write t is in hours because it was given to us this 2 hours half-life, so it's the same unit. So I will observe the way I do this, guys. I don't know how much, let's say I don't know how much I took, right? But I want 99% of that to go away. So what am I looking at? I'm looking at 0.01 of m to remain, right? I want 1% to remain and 99% to metabolize and be gone. So I will say I'm going to see 0.01 m, right, to remain, and then you have the rest of the equation.